everybody. So this is our paper where we are going to prove that Celeste is NP complete, and then later on showing that a modification in that leads to it being PSPACE complete. So first of all, gaming is difficult, but someone has to prove it and someone has to play it. So our main focus will be to show that the Celeste, it's a video game to show what complexity class it belongs to and go into detail of what it means. Okay. So first of all, a brief introduction on what complexity theory is. It's a study of complexity and complex systems and how the consumption of resources happens in the same. So a problem might be classified based on how it consumes the resources. So primarily we'll be talking about space and time of algorithms as resources. There is also randomness, which we have not looked into and can be done as a future work. So complexity helps a person to determine how difficult the problem is. So if a person wants to solve a problem, then the difficulty must be determined beforehand before investing resources into it. So it helps a society drive resources into the correct place so that there is no wastage. So we talk in terms of an abstract computational model. Usually it's called a Turing machine. So we'll be looking into that and seeing how it goes. So as termed by Scott Aronson, a computer scientist, there is a complexity zoo which classifies algorithms into different classes based on the resources they're consuming. So it is not very trivial to see how what a problem is and what kind of resources it will consume. It might consume polynomial or exponential resources. So starting off with something like solving chess, like you make a program that solves chess, you might think that is slow or fast. It's sure, it's trivial that it takes a lot of effort and complexity in time and space to solve it, whereas something as simple as sorting is fast, so it can be done in a fast way. But what about problems which are not very easy to determine? Something like a traveling salesman problem, which is popular. So right now it has been classified as NP complete. So it took a while to do the same. So we have a lot of theorems that help us determine the hierarchy that have been done previously in the computational complexity domain. So famously known time hierarchy theorem, space hierarchy theorem, and Savage theorem, which we will be using for proving the complexity of a video game, Celeste. But apart from Turing machines, there are a lot of other different ways that uh, the complexity is inferred, such as circuits and graphs. So, what is the relationship? So, P versus NP is already pretty famous and has been known to be one of the hardest problems and one of the most interesting problems that can be solved. Solving P and NP would lead to a lot of conjectures being disproven or proven. It can be said that it is very strongly supported that P is not equal to NP, but there has not been a proof for the past about 200 years. Okay, so now we'll see how the relationship between these objects are. So the Cook-Levin theorem states that you can convert any NP problem into a Boolean satisfiable problem. So that makes Boolean satisfiable problem NP complete. So this problem is known to be one of the hardest problems in NP class. So it is called NP complete problem. So what we see is that we can reduce any NP problem into Boolean satisfiability problem, making it NP complete. So if we are able to convert a problem to Boolean satisfiability problem, it's NP. Similarly, if I can convert Boolean satisfiability problem into a different problem, then that problem becomes NP complete. So if you are able to solve a Boolean satisfiability problem in polynomial time, that means we have solved P versus NP. Similarly, this conversion that I spoke before about a converting problem to a Boolean satisfiability problem is known as Garg's reduction. So what you do is you take an algorithm and its reduction and use that to solve a bigger algorithm. So this can be done in multiple ways, and to suggest that a problem is equivalent to another problem is to say that there is a reduction method to it. So if I say A reduces to B, then there is a reduction method that can convert your input of algorithm B to algorithm A. So if A is hard, then B is by default hard, because if you can solve A, then you can also solve B. So now we go into our main problem, which is to show that Celeste is NP complete. Showing Before showing that, we will see a little detail of game mechanics. So the character Madeline can move and dash, and she can also grab walls. There are other mechanisms in the levels, such as doors, which open by a button. So the button, if you press, the button stays inside and the door stays open. And then there is a platform that breaks if you stand upon and reforms if you leave it. Similarly, lastly, you have a space block where the Madeline can dash through, and the player kind of gets a speed boost and loses momentum. Finally, this is this work has been inspired by Eric Domain, who started this domain of classifying video games by classifying Super Mario Brothers as NP complete. So later on, he showed that you can generalize this proof and show that a few more additions to the game can make Super Mario Brothers P-space complete. So first, we show that Celeste is NP. So to show that Celeste is NP, we can see that if you give us a level, you can draw a path from start to end. So once the path is given, you can verify if this path is correct or not. So this verifiability makes it NP. Now, now that we have shown it NP, all that remains is that we show it as an NP hard problem, such that you can reduce any problem in NP to a Celeste, and then this will prove it to be NP complete. We will use three side reductions, which use three different clauses and variables. In each clause, there are three variables, and setting it to be any of them to be true will make the entire clause true. And the condition is that all the clauses must be true. So this is what Boolean satisfiability problem is, where you have different clauses and you need to set at least one in each clause to be true for all the clauses. Finally, we will show how you can break down this reduction into variable clauses and checks and crossovers to construct what is a level in for each Boolean satisfiability problem. So first, we will look at how we construct a variable gadget. So a variable gadget can be constructed by making the player choose two paths, true or false. So one gate corresponds to the other. And then we place a unbreakable or reformable platform on the entrance, such that if the player falls, then the player cannot come back. So which means the player's decision is sealed. Next, we see a clause gadget. Since we only require one of them to be true, we keep three parallel gates, such that if you open any one of the gates, it is equivalent of opening all. So any one clause, in the clause, if any one variable is said to be true, then you are solving the clause. Then we look at tunnels. So now there will be a lot of overlaps in the level. So we want to avoid Madeline going from one section to the other where it is not supposed to go. So we will put these space blocks that take away the control from the player and let it just flow. So using this, what will happen is if the player tries to make an illegal move, the player dies and the game starts again. So how does the transition happen from one variable to the other? So the transition happens by taking a path and then pressing the corresponding button and then going all the way up and dropping to the next one. Finally, once the player has completed all the variables, these sequence of doors open where each door will correspond to variable in a clause and three sets of doors will correspond to a clause. So if you have n clauses, then you will have n different sets of three doors such that at least one of them must be open. Finally, this is a simple level which we have constructed for the given Boolean expression. So the player will have to set at least one of them to be true, one of them to be false, and so on to solve this clause. By completing this level, the player will lead to the flag and solving the game. So if we can decide, if we can make a polynomial solver for Celeste, then you can solve 3-sat by constructing this level for every 3-sat. And since 3-sat is NP complete, you can solve any NP problem by converting it first into 3-sat and then from 3-sat to the Celeste level, which means that you can convert every 3-sat problem, every NP problem to Celeste by doing this reduction, which makes it NP hard. So Celeste is a game which is both NP and NP hard, making it an NP complete puzzle. The extension of a work is to show that you can make tweaks to the game and make it PSPACE complete. So what should happen when a game is PSPACE complete? PSPACE complete means all the algorithms that run for polynomial time. So the hardest problems in PSPACE are again PSPACE complete. So we show that Celeste with a slight modification becomes PSPACE complete. So what we do now is that we use another button, a red button, which can close doors. So this means that the complexity increases because now closing doors will mean that there is no direct path. You'll have to take detours and avoid closed button routes so that you can reach the end. We will again use a pre-established framework for showing that games are uh, a piece is hard. Since Celeste is a 2D game, we will continue using the same uh, mechanism. So this is the mechanism where we have similar clauses, but instead of variables, we have quantifiers. So you have there exists and for alls. So if we are able to construct this in Celeste using the extra mechanism, then we show that the game is complete. So the condition is that you need to you need to force the player into closing and opening doors so that the player has to make decisions of both closing and opening doors, making it harder. So what would happen is that by taking a path, you would not only open doors but also close doors. So taking a path is not as simple as just opening all the doors. This means that what path you take now matters more, and you might have to take the path multiple times. So the traversal is that a clause can only be traversed if at least one of the variables is set. So if you have n clauses, then at least n variables must be set. And if the player can cross all the clauses, it means that the clauses are satisfied and the Boolean formula has also been satisfied. So how do you force the player into closing doors? So what we do is we make paths such that the path can be only taken if the door if the button is pressed. So if the button is pressed, the door will get closed. So Madeline cannot pass through until the button has been pressed. This way, we can force the player to press the buttons that close doors so that there are consequences of taking a path. So by this, we construct tunnel gadgets, which was the core to the construction for PSPACE completeness. But what changed? Addition of this button made it such way that the player would have to keep track of what door has been opened and what door has been closed. Earlier, if a door has been opened, it will remain open forever. So the state is simple. Here, the state becomes more complex since you have closing of doors. So keeping track of this will blow up the complexity from NP to P space. So the lack of knowledge about the status of the doors makes the game P space complete. In conclusion, Celeste originally is NP complete, but uh, if you add a feature of closing doors, then it becomes P space complete. So what we learn from this is that games, they are just mathematical models that act as a bridge between mathematics and real life. Real life is very complicated to be modeled directly. Instead, we can try our modeling on video games and see that a lot of times video games serve as a good medium to represent algorithms and their efficiency. This is why a lot of artificial intelligence is focusing on solving games where AI is trying to beat humans in video games. Thank you.